Welcome to Dr. Jed's continuing series on calculus videos. Section 3.5 of Rogowski is today's lesson, higher order derivatives. So first we're going to talk about the notation, what it means, how you'd write it out. Then we'll do some examples, 3 examples specifically, and then maybe also a graphical consideration example, sort of what these higher order derivatives, particularly the one that follows the first derivative, what that means on a graph. And then we're going to introduce you to the concept of differential equations. This isn't necessarily in the book in this section, but it's a useful thing, and now that we have higher order derivatives, we can actually talk about it. So, first, notation. What is the derivative of a derivative? Well, a function, if the function's f of x, the derivative is f prime of x. So, naturally, this is a function. We can take its derivative. I don't mean we do it by limits. We have all sorts of rules. But the derivative of that, so the derivative of the derivative, you could write it this way, but that's awkward. So notationally, we usually write, instead of f prime of x, we write f double prime of x. And instead of writing the derivative of the derivative, we write the second derivative. And you might guess that if we're going to talk about second derivatives, we also talk instead of derivative, we'll talk about first derivative. We can also talk about the third derivative. And I'll bet you can guess what the notation would be. It would be the same thing, but with 3 primes. We call it triple prime. We could talk about the fourth, the fifth, the sixth. How about the 30th derivative? I'm not even sure how you spell 30th, but there we go, 30th derivative. I could write this. I could write f and then 30 primes. But that's not a pretty thing. And to be honest, can you tell? Did I write 30 of them? You can count carefully if you want. Maybe it's 29. Maybe it's 31. So that's not a good notation. A better notation, we write f parentheses 30. That way, it says there are 30 primes. We just didn't want to write them all out. You could write that up here as f parens 2. But let's be honest, this is slower. It takes more writing than this does. So you'd only start really the parentheses when it becomes awkward to write out all of the primes. Now there's also the Leibniz notation. How do you write in that notation? This was dy dx, or df dx. This will be, well, there's a 2. So in order to do this, instead of dd doesn't work. So it's going to be d squared y over dx squared. We're taking the derivative twice of this, where that's the variable. This then, as you might imagine, is d cubed y over dx cubed. Notice that the 3 is a different spot on the top and the bottom. Why? Because there's a dx, 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 and this is not dy times dy times dy, even though this isn't actually even times or divide. They want to notate that. It's doing this 3 times with that being the variable 3 times. So let's do an example. Here's a function, a polynomial. I'm going to take its derivative and so forth. Its first derivative, 10x to the 8th plus 4x to the 6th minus 2x to the 4th plus x squared minus 2. I take the derivative. What do I get? I get 80x to the 7th plus 24x to the 5th minus 8x cubed plus 2x, and then that goes away. That's the derivative. How do you take the second derivative? In this case, it's really easy. I do it again. 560x to the 6th plus 120x to the 4th minus 24x squared plus 2. Let's do it again. Now the numbers are big, but that's not hard. Let's see. This is going to be 3,360 x to the 5th plus 480 x cubed minus 48x. That goes away. Let's do one more. This one I'm actually have to think about. 16,000, 800 x to the fourth plus, what's that, 1440 x squared minus 48. And, okay, I can keep going for a while. Let's skip down to the 10th one. This could be awkward, but you know what's happening to each of these terms? This one disappeared right away. This one disappeared in the next step. This one's going to disappear again. Eventually, all of these terms in polynomials go away. So this one down here, without having to do much computation, is going to be 0. Let's talk about another example from motion. You may recall this height problem from before, from the previous day's work. We had, the height was minus 4.9 t squared plus 63t plus 120 meters, where t is in seconds. The derivative was the velocity. So the second derivative will be the derivative of that. And the derivative of velocity, change in velocity. Stop and think for a second. If you're going 30 miles an hour in a car, and you want to get to 40 miles an hour, what do? Well, obviously you press on a pedal, but you accelerate, don't you? So the derivative of velocity is acceleration. And we'll use a of t for that. So, a of t is the derivative of the velocity, which is the second derivative of the height. Now, keeping in mind that pieces go away, when you take the second derivative, well, this is going away in the first derivative, but this one will go away in the second derivative. So what happens? Because in the first derivative, well, let's just write it out. The velocity will be minus 9.8 t plus 63. The acceleration, then, is the derivative of that, is minus 9.8. Now, the units are going to be the units of the y, so meters, divided by the units of the x squared. Why? Because it's really the units of velocity, which were meters per second, divided by the units of the x-axis. So it's meters per second per second. Now you might wonder, is there anything beyond this? And there is. So the derivative of that well, I'll pause for a second. Why would you need it? If you look at this, the derivative of that's 0. If you just use Newtonian mechanics, force equals mass times acceleration, force controls the world, there's not going to be any need for a third derivative. But if you add frictional coefficients in there and more complicated things, you need another word. And this word wasn't really around. So in the 1960s, when they started talking about it in the development of a moon launch, they needed a word. So the word they used, they decided, what is a sudden change? So they used the word jerk. So the jerk is the third derivative of position. In this case, it's 0. I can give you another example where you find it, but it's just, that's what it's called. Now, speaking of these words, acceleration, velocity, and so forth, how does this all relate graphically? So here's a graph of a function. So if this is y equals f of x, what is the derivative? The derivative is the slope of the tangent line. So it's positive here, right? So right here, f prime of x is pretty big. If we look over here, the slope is no longer as big. It's still positive, but it's not as much. So I'll say it's close to 0. So what's happening to the derivative? It's changing from very positive to not much at all. It's getting smaller. So the second derivative is negative. Notice, the function's still getting bigger all the way, but it's not getting bigger as fast. So the second derivative is the change in the first derivative. It's negative, meaning we're getting less and less and less of the first derivative. Not as much slope going up, less, that means the second derivative is negative. That's an example. We'll study this more later in the semester. This is just a feel for what it means. So now, I want to introduce another concept, differential equations. What is a differential equation? In the simplest terms, a differential equation is an equation involving the derivative. So we'll just give an example. So we want to show that this function, y equals x e to the x, satisfies this differential equation right here. How do you show it satisfies that? How would you show it works? Well, find what y double prime is. This is y double prime minus 2y prime plus y equals 0. Find what these things are, put them together, see if it works. We know y equals x e to the x. What's y prime? Well, that's a product, so we need the product rule. So it's the derivative of x times e to the x plus the derivative of e to the x times x, or it's x plus 1 times e to the x. What about the second derivative? I can take the product rule of that, but honestly, if you see the pattern, what I'm going to get, if you work this out carefully, is I'm going to get x plus 2 e to the x. That's product rule work. Work it out if you're not sure. If you have any questions, of course, ask your professor. But let's try it out in that equation. Y double prime minus 2 y primes plus y. What's that equal to? Well, I get x e to the x. I have 2 e to the x. I have 2x e to the x with a minus sign. And minus 2 e to the x. And then plus x e to the x. Let's cancel it all out. What do I get? X e to the x? X e to the x, that's 2 of them. Minus 2 here. There's 2 here. There's 2 there. Look what happens. It's all equal to 0. This does, in fact, work. This does satisfy the differential equation. Now, what does that mean? How do you find solutions in general? That's much more complicated. It's not for us right now. But this is how you could use differential equations right now. Until next time, this is Dr. Jed.